Our universe is such an alluring and vast space and is filled with many beauties such as planets, galaxies, and stars. The universe is also filled with components that we are not very familiar with yet, such as dark matter. Even though we know it exists and it is a huge segment of our universe, we have much to learn. Today, we will be discussing the enigmatic existence of dark matter. The observable universe is approximately 13.7 billion light years old. That means that you would be traveling at the speed of light, 186,282 miles per second, for a year. Traveling at that speed of light is impossible for us at this point in time unless you're traveling on the Millennium Falcon from Star Wars or the TARDIS from Doctor Who. But you may ask, how do we measure the size of the universe? It is calculated by seeing how far the light of the farthest star is shining. The light of the furthest star has traveled approximately 13.7 billion light years. At that extent, the Earth is an itty-bitty speck of sand on a gargantuan shore. There's so much exploration that has been done by using very powerful telescopes such as the Hubble telescope or Paranal Observatory, but there is so much more to be discovered. So you may be asking, what is dark matter? Well, that is a very good question, my friend. We don't know. We don't really know what it looks like or what it is, but we know that it exists and that there's a buttload of it in the universe. In fact, we know that the universe is filled about 25% of it. This is sort of why it has the name it does, because we don't really know what it is and its physical properties. However, before we dive into what we think it is and what we know it's not, let's begin with some history of how it was discovered and how we know it exists. Let's begin by explaining the history of how dark matter came into existence. In 1932, Jan Hendrik Oort, a Dutch astronomer, observed that in our adjacent galactic neighborhood, the stars were moving much faster than what the computations foretold. His computations were also unfortunately found to be incorrect, but Oort was definitely onto something. Fritz Zwicky was a Swiss astronomer who was not only remembered for his benefaction to science, but also his blunt and brusque personality. In 1933, he analyzed the Coma cluster in one of his papers. In the paper, he deduced that with the theorized amount of matter at the time, the galaxy should be flying apart. Therefore, there should be a much greater amount of matter in the galaxy than expected. He said, and I quote, "If this would be confirmed, we would get the surprising result that dark matter is present in much greater amount than luminous matter." This is exactly what astronomers theorize today, even with the lack of knowledge of the exact contents of dark matter. It is hypothesized that because of his infamous personality, his work wasn't taken as seriously as it would have been. But we are very thankful for his persistence anyways, because he has made a huge step for astronomers in the journey of exploring the history of the universe. The next astronomer that also made a huge contribution in the exploration of dark matter, and even though her personality didn't affect her lack of recognition, but unfortunately her gender, Vera Rubin, a very accomplished American astronomer, developed and made even more progress on the exploration of dark matter. In 1968, Rubin and Ford were in the Kitt Peak Observatory and noticed that the outermost galactic spirals were moving as fast as the innermost stars. This is the rotation curves of the galaxy. At the rate they were traveling, they should have flown apart. Rubin came to the conclusion that there must be more matter in the universe than we can see. The first piece of evidence we have that we know dark matter exists is the rotation curves of the galaxies. Let's take, for example, the planets in our solar system. If we measure the velocity of the planets that are closer to the sun, we see that they travel faster. But the planets that are farther away from the sun travel slower. This is also due to all the mass that is in the center of the planets and the sun. It's in accordance with Newton's second law that force is equal to mass times acceleration. Since the sun has an extreme amount of mass, the planets close to it have more velocity. So in terms of galaxies, you would think that the same thing would apply. Since the force is much stronger in the center of the galaxy, the farther out you travel, the galaxy should move slower. It's not the case, however, which is very shocking. This is what Vera Rubin discovered. So there must be extra matter because the equation used to measure the rotation curves, the farther the distance from the core, the less velocity there should be. According to that same equation, the only logical explanation that comes next is that there is more matter. The second piece of evidence are the coma clusters. This is what Fritz Zwicky was observing and exploring. The coma clusters are similar to the rotation curves of the galaxies. The coma clusters' outer disks are moving much faster and should be repelling each other. The random velocities of these cluster galaxies suggest that matter is what's moving them so fast and not flying away from each other. The third piece of evidence that we have explores mass instead of motion, like the other two evidences. Based on Einstein's theory of relativity, light is able to bend around large masses. The larger the mass, the greater the distortion of light. So what was discovered and observed is based off of light bending, which was gravitational lensing. When a galaxy is in front of a supernovae, a formation called the Einstein ring is created that is generated by the gravitational lensing. So this single supernovae that is behind the galaxy creates an illusion of 4 or more specks around the galaxy. This light bending suggests that there is matter around the mass of these galaxies because the more matter there is, the more light bending. This has been seen with multiple galaxies, not just 1 or 2. All of this evidence points to dark matter. A fourth piece of evidence that shows us dark matter is the bullet cluster. The bullet clusters were 2 clusters of galaxies that collided with each other, and the gas surrounding it slowed down, but the dark matter did not. The dark matter emitted no light and was separated from the regular matter. If you look in the picture, you will see there is red or pink surrounding the clusters. This is the gas, and it is shown through the X-ray spectrum, and you see that it is surrounding the cluster. The blue cloud that surrounds it is a simulation of what we think the dark matter would be based off of the charts that we've made that shows the distortion of the weak gravitational lensing. Since then, we now have observed multiple clusters that exhibit this behavior. So now you may be asking me, where does this dark matter come from? Well, dark matter was created in the first second after the Big Bang. We can see this in the cosmic microwave background, or CMB. This is the electromagnetic radiation that was formed in the early universe that emits radiation. The CMB was first discovered by Penzias and Wilson, who were radio astronomers. They noticed that anywhere they looked in the universe, they were surrounded by noise. They thought at first that maybe their apparatuses were being affected by other types of microwaves, but eventually the CMB was discovered. As you can see, there are little dots all over the place with the CMB, and they may look like static, but they are not random. The little normal matter relies on dark matter and dark energy to hold it up and not collapse on itself. In a sense, it's almost like an arch that holds a bridge up, but instead it's holding the universe up. There has also been a successful experiment that showed more attributes of dark matter. There was an event where this star bent its light inwards and created a microgravitational lens, making it much brighter. Stars can become brighter, but they also change color when they become brighter. This star, however, didn't change color, but it was observed that something passed in front of the star and caused this microgravitational lensing. Even though it's suggested that this is dark matter, this hasn't been replicated enough to be considered sufficient evidence. Dark matter also has a few properties that we know of. It does not absorb, reflect, or emit light. It doesn't interact well with normal matter, and it's a WIMP, or weakly interacting massive particle. Because of all these attributes, it's very difficult to detect. I have a hunch of what dark matter could be. There have been many ideas as to what it could be, some more imaginative than others, but there have been many scratched off the list. Some think it could be machos. Machos stands for massive compact halo objects, and these could be black holes, stars, or even planets. These are things that we can observe. However, we have not yet been able to detect this matter, making it less probable that these are machos. But particle physicists have a few promising ideas, and the most common ones are neutrinos and axions. Neutrinos are subatomic particles that have no electric charge, very little mass, and interacts through weak nuclear force, which makes it very hard to detect. It can easily go through things without being detected, almost like ghosts. Another common particle dark matter is associated with are axions. The axions' existence has not been fully proven, but they don't really interact with normal matter, they do have mass, and they don't emit light, making axions have similar properties to dark matter. But we know that these particles exist through other associations it's had with normal matter. Astronomers crossed out particles that come from baryonic matter, like protons, neutrons, ordinary matter, as those don't have the properties of dark matter, but we still have no idea what it could be. There are a few mechanisms we now have to help us possibly detect dark matter. There are three main apparatuses doing this. First, we have the xenon or LUX experiment. Xenon is an underground dark matter detector. The reason LUX is underground is to provide a very quiet environment, meaning to protect it from the waves of the world above, and this is to possibly capture dark matter. Since dark matter is a WIMP, there is a possibility that there isn't a sensitive enough detector to capture it yet. Another experiment in Switzerland is trying to create dark matter. This is the CERN, which is a hadron collider that is recreating the conditions of the Big Bang. With the vast machine that spans 16 miles, we are trying to detect any properties of dark matter. The CERN collides proton beams together through its cyclical formation to see what particles are generated. Then there's the Fermi Gamma Ray Telescope, which is in space in the hopes that dark matter will collide and leave a trace of light behind. Our universe is such a fascinating place that has a beautiful tale to tell. As I mentioned before, we have many things to decipher and discover, and we're on our way there. I know that there are a lot of questions that are still unanswered, but I hope that I have convinced you that dark matter exists and that it's really freaking cool. The discovery of the physical components of dark matter will have a huge impact in the scientific world. It might even change physics as we know it today. Researchers are working tirelessly to find these answers, and with the devices we already have, we are really hoping to find even more solid evidence. Hopefully, we will have our answer so we can learn more about our universe's past. I also have linked below some other YouTube videos that have wonderful explanations of dark matter if you want to gain even more knowledge about dark matter. Thank you so much for joining me today and finding out more about dark matter. I really hope you enjoyed this video, and I hope you have happy holidays and a wonderful rest of your day. Bye!